In this presentation, we will look at combining components of impedance in series and in parallel, and specifically we will add all different kinds of components. So up until this point, we've looked at a resistor and a capacitor connected together, a resistor and an inductor connected together, but we haven't looked at what happens if you connect just an inductor and a capacitor, or what if you have all of these components connected in a circuit. So just as a quick refresher, reminder, impedance, we know how to write the impedance for a circuit, and we know how to write it for specific components. So we know how to write the resistive impedance in terms of the resistance and the angle. We know how to write the inductive impedance as the inductive reactance with an angle of 90, and we know how to write the capacitive impedance as the capacitive reactance with an angle of negative 90. So all of that is still valid. Everything we've talked about so far we can still use. Our impedance diagram is also still valid, so we can figure out the total impedance in the circuit by adding the resistive and the resistive piece and the reactive pieces squared, taking the square root. What we're going to find is that in our circuit, if we have a capacitor and an inductor, that one of those two components is going to actually dominate in the end in terms of our end result. So everything we've learned so far about impedance diagrams is still valid. We're just going to add another piece to this in terms of having multiple components. And we're going to analyze circuits that are a little bit more complex, but just using the techniques that we've used in the past for analyzing circuits that are in series and parallel for resistors. We remember that in terms of series connections that the impedance adds together, so the total equivalent of impedance of components that are connected in series just adds together. The current through all those components has to be the same, but the voltage would be different if the impedance values were different. Of course, we can always use Ohm's law equivalent for AC, and we can use the voltage divider rule for components that are connected in parallel, where the Vx is the voltage across any one of these components, Zx is the impedance value of any one of these components, Z total is the total equivalent impedance, and then the total voltage across those components. Additionally, if we have components that are connected in parallel, Kirchhoff's current law has to be satisfied, so the current entering the junction has to equal the current that's passing through each of the components. We found that the impedance values add as the reciprocal, and that we can use the current divider rule. So the current through any particular component is just the total impedance, where that impedance was added as the reciprocal, over the impedance of the component that I'm interested in knowing the current through, and then multiplied by the total current. We want to keep in mind that all of these expressions are in phasor notation, so we have to treat them as phasors when we add, subtract, divide, and so on. And of course, the other thing is that components that are connected in parallel all have the same voltage across them. All right, so let's look at an example where we have three components that are connected in series. I have a resistor, an inductor, and a capacitor, and I'm given the resistance value, the inductive reactance value, and the capacitive reactance value. And I'm asked to determine what is the total equivalent impedance for these components that are connected in series, and what is the total current that would flow through all of these, and since they're connected in series, that current would be the same, and then what is the voltage across each one of these components. So the first thing that I would want to do is I would want to write down the impedance values for each of these components. So the resistor has a resistance of 25 ohms. So the impedance is 25 ohms with an angle of 0. The inductor has an inductive reactance over here of 200 ohms, so its impedance would be 200 with an angle of 90, and written in rectangular form, this is just an imaginary part of 200. And then the capacitive impedance would be the capacitive reactance, which is given as 225 with an angle of negative 90, and in rectangular form, that's a negative 225. So because these components are connected in series, I can figure out the total equivalent impedance by adding these values together. Remember that in series, the total equivalent impedance is just the addition of the values. So I need to add them in rectangular form, so I would have 25 ohms plus an imaginary part of 200 and an imaginary part of negative 225. So when I add these values together, I only have one real part, which is the 25 ohms, and then when I add the imaginary parts, I get a negative 25 ohms. In rectangular form, I've got the real part and the imaginary part. I can convert that into the polar form, and we know how to take a complex number from rectangular form and convert it into polar form, and I get that the total equivalent impedance in this circuit for these three components is 35.4 ohms with an angle of negative 45 degrees. The other thing that I wanted to point out here is that the total equivalent impedance implies that I have some resistive piece, and it also implies that I have a reactance piece, but because this is negative, it means that the inductor is not dominating, but instead the capacitor is the component that's dominating. So the fact that this is negative means that that capacitive reactance, which is larger than the inductive reactance, is dominating over the circuit. And it looks like, when I look at the total equivalent impedance, that I have a resistor and just a capacitive reactance component, if I just looked at the total equivalent impedance together. So we'll come back and we'll talk about that a little more later, but just looking at this, we can kind of see how much of the circuit is resistive and how much of it is reactive in terms of either capacitive or inductive. Once I know what the once I know what the total impedance is in the circuit, I can calculate what the total current is according to the equivalent of Ohm's law. I take the voltage total across those components and I divide by the total impedance. The total voltage is given to us as 10 volts with an angle of 0. The total impedance is 35.4 ohms with an angle of negative 45. 10 divided by 35.4 gives me 0.283 amps. And then 0 minus a minus 45 degrees gives me a 45 degrees. So my current in this case is leading the voltage. The voltage was at 0 degrees. The current is at 45. So the current is leading the voltage by 45 degrees. And that makes sense according to our impedance angle of negative 45, which tells us that the voltage is lagging the total current by 45. Once I know the current in my circuit, I can use the equivalent of Ohm's law for each of the components, and I can figure out what the voltage is. So the voltage across the resistor would be the current times the impedance of that resistor, so 0.283 amps, phase angle of 35.4 times 25 ohms, and I get 7.07 with an angle of 35.4. So I note that the voltage across the resistor and the current through the resistor are actually in phase with one another, which is what I would expect for the resistor. I can find the voltage across the inductor by taking the current times the impedance of the inductor. So I have my current, I multiply by my impedance for the inductor, which is 200 with an angle of 90. I get 56.6 and an angle of 125.4 when I add those two angles together. So one of the nice things, or one of the interesting things about this, is if you look at the voltage supply, the voltage supply is only 10 volts, but yet I have a voltage across the inductor which has exceeded 10 volts. So let's figure out what the voltage across the capacitor is. So the voltage across the capacitor is just the current times the impedance for the capacitor. So here's my current, and here's my impedance for my capacitor. And so when I multiply those together, I get that the voltage across the capacitor is 63.7 with an angle of minus 54.6. So I realize that my voltage across my capacitor is actually lagging behind the current, which is what I would expect. So let's just look at the numbers out front, right? So I have this, this supply, or the input voltage is 10 volts. And the output voltage for the resistor is around 7, but the inductor is 56. It's much larger than 10, as is the voltage across the capacitor. It's 63.7. So you might be wondering, how is it possible that I can get a larger voltage across the components than the voltage that I have that's being input? And the reason that that can happen is because you have an inductor and a capacitor in your circuit. And so what has happened is that if you look at these values for the voltage across the inductor and the capacitor, they are actually out of phase with one another by 180 degrees. So what that means is that when the voltage across the inductor is a maximum, the voltage across the capacitor is a minimum. So when the voltage across the inductor is a maximum, it would be a plus 56.6, and at the same instant in time, the voltage across the capacitor would be a negative 63.7. And they are always, in terms of maximum values, they are always out of phase with one another. So it makes sense that Kirchhoff's voltage law is still satisfied at any given instant in time. If I add these voltages together, I am going to get 10 volts, essentially, at any given instant in time. But it's possible for individual values to be larger than 10. Now this is a little bit hard to do because these angles are not, they're not set up at exactly 0, but the idea is that when the voltage across the inductor is max, the voltage across the capacitor is a min. And so they will always have essentially, for the maximum values, the opposite signs. So it's okay if you get voltages that are larger than the source. Previous presentations sort of already mentioned this, but if you have two impedance values that are in parallel, one way, instead of using the reciprocal notation, is just to use this special formula where you multiply the impedance values and then divide by the addition of the two. And so we've used something similar to this, I think, with resistors in parallel. It only works for two components in parallel, and we do have to use Phasor notation, so we have to treat them as complex numbers and add them that way. So the reason that we're bringing this up is specifically because we could look at having an inductor and a capacitor connected in parallel, and there's sort of a special case that can happen. So if you have a capacitor and an inductor that have exactly equal reactance values and they're placed in parallel, then what happens is that the equivalent circuit of those two components behaves as an open circuit. So let's look at how we would approach this. So I've got a capacitor that has a capacitive reactance X, whatever that is, it could be 100 ohms. And I have an inductor that has an inductive reactance that has exactly the same value for the reactance X, or let's say 100 ohms. And they are connected in parallel. So if I look at the previous expression for how I can connect components in parallel and find the total equivalent impedance, I would multiply their values together, and then I would divide by the addition of the two. So for an inductor, the impedance is the inductive reactance with an angle of 90, and the capacitor is the capacitive reactance phase angle of minus 90. Both of these reactance values are exactly the same value for X, so that's why I get an X squared here. And if I take the angles, here if I'm multiplying these two complex numbers, I would add the angles and I would get a 0. On the bottom, I would have to add their impedance values. The inductor is an imaginary part that's positive. The capacitor is an imaginary part that's negative. I'm adding these two quantities together. They have the same reactance values. These are both X. So if I take this and subtract the same thing from it, I get 0. If I divide anything by 0, essentially I have infinity, right? So what this is saying is that if you take a capacitor and an inductor and you put them in parallel with one another in a circuit, and they have exactly those same impedance values, it behaves as if it has an infinite amount of resistance in the circuit, right? Because the impedance is measuring how much those components resist the flow of electricity. And so that impedance value can be, it goes to infinity, and an open circuit is equivalent to an infinite resistance. You can't have any current flowing through it. So we do have to keep that in mind in terms of connecting components in parallel, that we can actually produce an open circuit under certain circumstances. So just as a quick example, let's consider two impedance values that are connected in parallel that just have inductance and capacitance. So I have an inductor that has a reactance of 200 and a capacitor that has a reactance of 250, and I have current that's entering the circuit, and that current is 2 amps. And I want to determine what is the current through each of the branches. So the first thing I would want to do is write down what the impedance value is for each of the components. So for the inductor, it's 200 ohms with an angle of 90, or an imaginary part that's positive. And for the capacitor, it would be 250 ohms with an angle of minus 90, or a negative imaginary part of 250. These components are connected in parallel, so I am going to find the total equivalent impedance by multiplying the two impedance values together and then adding them together and dividing by that quantity. So 200 with an angle of 90 times 250 angle of negative 90, that's multiplying those two components together, and then I would add the two values together at the bottom. When I multiply, I get 50,000, and then ohms times ohms is ohms squared, and then the angle, of course, is 90 plus a negative 90, which is 0. On the bottom, these are both just imaginary pieces, so when I add them together, I get a negative imaginary part, and it's 50 ohms. I can convert the bottom from rectangular form into polar form, and since it only has an imaginary part, the angle is a negative 90. And now I can actually divide these quantities and find the total equivalent impedance. So 50,000 divided by 50 is 1,000, and then 0 minus a minus 90 is a positive 90. So I have these two components, an inductor and a capacitor, and they're connected in parallel. Individually, they have reactance values of 200 and 250. And yet, when I combine them together, the total equivalent impedance, which is the resistance to the circuit, is much, much larger, right? It's 1,000. So 200 and 250, and I'm getting an impedance value of 1,000. So this kind of goes back to that last discussion. So the closer that these two reactance values are together, the larger the impedance is going to be in that circuit for those two components that are connected in parallel. Because eventually, if they were exactly the same thing, this impedance value would be infinite, and there would be no current that could flow through that circuit, because it would be essentially equivalent to an open circuit. All right, so I know the total impedance in my circuit is now 1,000 ohms with an angle of 90 degrees. This also means that in this circuit, the inductor is dominating, and that kind of should make sense because the reactance for the inductor is less than the capacitor, so it's dominating because, in terms of, this is the piece that has less overall resistance in the circuit. All right, so now I've figured out that these two components together are equivalent to one total equivalent impedance, and I can calculate the current through each of these sections by using the current divider rule. So if I wanted to find the current through section 1, I would take the total equivalent impedance, which was 1,000 ohms with an angle of 90, divide by the impedance of this particular piece, which is just the inductor, which was 200 angle of 90, and then multiply that by the total current that's entering that junction, which is 2 amps with an angle of 0. And I end up with a current that's passing through that inductor of 10 amps and an angle of 0. So again, I'm starting off with 2 amps going in, and I'm able to get 10 amps going through that inductor. Somehow that should red flag should be, going off. Like, is something wrong? Because that's not how things worked before. And the answer is nothing is wrong. It's okay. So if I find the current through the other section where I have just a capacitor, I could go through the same process. The total equivalent capacitance is 1,000, angle of 90. The capacitive impedance is 250 with an angle of negative 90. And then the total current, again, is still 2 amps. So when I plug those values in, I end up getting 8 amps. And 90 minus a minus 90 is a 180. So the thing that you have to realize with this is that the current through the inductor is exactly 180 degrees out of phase with the current through the capacitor. So what does that mean? Well, Kirchhoff's current law is still valid. So the current that's entering has to equal the addition of these two currents that are exiting. So if I think about this, this one is much easier to show. I have 10 amps at an angle of 0, 8 amps at 180. So if I write these in rectangular form, this would be a real number, right, just 10, and 180 is a real number that's negative, so I get 10 amps plus a negative 8 amps, which of course is just 2, which gives me back the total that I had before. So similar to the previous examples that we saw, it's possible that you can have current entering a junction, and the current through an individual component, the maximum current can actually be larger than the current that's entering, because it's in parallel with another component that's out of phase with it, and when one of them is a maximum, the other one is exactly a minimum, a negative, and when you add those two values together, they do give you what the source is. So this is what makes AC circuits probably a little bit more complicated, is our intuition from what we learned about resistors in series and parallel tells us that we should be able to look at these numbers and be able to see what's going on. And we can do that. We just have to really think about the fact that these are not just real numbers, they're phasors, and we have to treat them as phasors when we're adding them together.